So today we will discuss another application of definite integral. So we will have volumes. And for today's session, we will discuss two methods, actually three methods. Um, One of them is the method of disks. The other one is the method of washers. So we will focus on these two methods. Okay, but I will give another method at the beginning, okay? Because the method there, it's actually somewhat prerequisite or maybe an introduction to these two methods here, okay? So let us define what right cylinders are. So a right cylinder, it is a solid that is generated when a plane region is translated along a line or axis that is perpendicular to the region. So for example, in here, you have this square, okay? So think of it as a very thin square. And then you move it. So this guy here, it's vertical. So you move this square horizontally, okay? So the motion is perpendicular. Okay. So what we will get here is a rectangular box or a parallelepiped. Okay. So in here you see a triangle. Okay. Again, it's vertical. So our motion is horizontal in here. What we will get is a triangular prism. Okay. And then here we have a circle. Okay, again in vertical position, and then we move it from left to right. So we move it horizontally. What we will get is a circular cylinder. Okay, and in here, um, if you don't see it clearly, what you have here is called a washer. Okay, it's called a washer. So it is like there's a circle in here, and then there's another circle inside that. They are concentric. Okay, meaning they have the same center. Okay, so what we have in here, we consider the region in between the two circles. Okay, so we have a what we call a washer. Okay, so if you move this um, washer here horizontally, what we will create is like a cylinder, but there's a hollow in the middle. Okay, so it's a cylinder, but there's a circular cylinder, but there's a hollow in the middle. So it's like a tube. Okay, so we will be able to create a tube. So we call all of them right cylinder. Okay, so our problem is how do we get the volume of these right cylinders? Okay, so if a right cylinder is generated by translating a region of area A through a distance h, okay, then we call h the height of the cylinder, okay, or sometimes we call it the width, okay, and then the volume of the cylinder generated is defined to be the area, okay, the area of the region that you have multiplied to h. So in here, you have some region here with area A. You move this region horizontally, a distance h. You will be able to create a right cylinder, okay? And the volume of that right cylinder will be equal to the area A times h, okay? So questions so far? So in here, we have a fixed region. We have a fixed region and we just move it, okay? We just move it um, in the direction perpendicular to the plane of the region. So this one is vertical, we moved it horizontally, okay? So the volume can be calculated using this formula. Okay? But what if at some point on this, maybe you have the motion here, you have this axis here, okay? You have this axis here. At some point in here, the region became bigger or the region became smaller, okay? And maybe at some point here, the region became larger or smaller, okay? What I'm saying is, what if the area of the region changes as it moves, okay? For example, in here, at this point, we have a small, if we look at this part here, okay, we have a small, possibly, um, region in here. And then we move further to the right. Say here, we have a bigger region. Okay. So how do we solve for the volume of the cylinder? Okay, or of the solid. Okay. So let S be a solid that extends along the x-axis, okay, and is bounded on the left and right respectively by the planes that are perpendicular to the x-axis at x equals a and at x equals b. So we have this solid, we lay it flat on the xy plane, maybe, okay, or on the floor, okay, and then you get the leftmost side of your solid that will represent your x equals a, and then you get the rightmost side of the solid that will represent your x equals b. Okay, so our problem is to find the volume of the solid, assuming, take note of this, assuming that its cross-sectional area, we will define that to be a of x, is known at each x in the interval ab. Meaning, if you got this, okay, if you got this cross section here, okay, you know what the area there, you know what the area A there, okay. If you got this here, this part here, okay, you know also the area, the exact area there. And on the rightmost side, you know what the area is. On the leftmost side, you know what the area is. Everywhere, okay. And suppose it actually depends on the location. That's why we have here a of x. Okay, so how do we find the volume of this solid? Now, as you can see in here, in this illustration here, okay, we 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 will divide the interval AB into n subintervals. Very much similar to what we were doing from before. Okay, and then you pick this blue guy here. Okay, it has some thickness. Suppose you get that, and you will have this blue part in here. Okay, this blue part in here. So it's a solid. We call it a slab. Okay, so you will have a slab of this whole solid. Okay, what we're going to do is to approximate the volume of this slab. Okay, and our approximating slab will be a rectangular box or a parallelepiped. Okay, and then what we're going to do is to add all those rectangular box or slabs, okay, that will approximate the volume of your solid. Okay, and then we will let n approach infinity so that we will have thinner and thinner and thinner slabs, and that will better approximate the solid. And as n approach infinity, we will have the actual volume of the solid. Okay? So you remember all these steps? This is what we were doing since we started discussing area problem in the definite integral. So we fix n, and then we divide the interval AB into n subintervals. It can be any length subdivision, but in this case, to simplify our computation, we will divide the interval into n subintervals of equal length. So our delta x will just be b minus a over n, or the kth slab will have um, thickness delta x sub k, okay, which is the same as the delta x because the subdivision is of equal length. And then for the kth subinterval, we choose a sample point. Okay, for example, in here, this is our kth subinterval. We choose a sample point. Okay, we choose a sample point, and then we evaluate this sample point on the area function. That's what we know. Okay, the area function gives you the area at that particular cross section. And then using that, you construct the rectangular box with that length and width. Okay, so this is your cross section. So this guy here, it's the cross section. You would know the length and the width of this, or the length and the height of this cross section. Then you construct the rectangular box with the same length and width as this guy here, or the same length and height as this cross section here, and the width or the thickness of your rectangular box will be delta x sub k. Okay, and then the volume of this kth slab, okay, will just be approximated. Okay, the volume of the k slab will be approximated by the right cylinder. This is just your rectangular box, so it's a right cylinder. Okay, the thickness is delta x, that's your width here. And of course, the cross-sectional area, we know that to be a of x sub k star. Okay, so that will be the volume of this rectangular box. It will approximate the slab of your solid, this guy here, this blue so this blue part here. Okay, so if we add the approximations, we will have the Riemann sum, and the volume is approximated by that Riemann sum. So the volume is approximately equal to the sum A of x sub k star delta x, where k runs from 1 up to n. Okay? And of course, if we let n go to infinity, we will have the actual volume. Okay? And of course, provided that the area function here, provided that the limit here exists. Okay? Provided that the limit exists. Of course, if your area function, it's a continuous function, then the limit will exist. Okay? Questions? So again, the solution to this volume problem, it's very much similar to the one with the area problem. They were all derived from that, or the solutions were very much similar to their mother, definite integral. Okay? So let S. So let us give this definition. Let S be a solid bounded by two parallel planes perpendicular to the x-axis at x equals a and x equals b. If if for each x inside the interval AB, the cross-sectional area of S perpendicular to the x-axis is A of x, then the volume V of the solid is given by this, okay? Provided that your A of x is integrable on AB, meaning provided that this limit exists. So let us consider this example. We want to derive the formula for the volume of a pyramid with square base of side length S and altitude H. So let us visualize the situation. So suppose this is your Cartesian plane, okay? And then let's look at it in the three-dimensional space. So, so you have the pyramid that will look something like this, okay? So let me try to draw that one. We have something like this, then in here, then somewhere here, okay? Then we have this, change that, okay? Okay, so the pyramid will look something like this. Um, if we try to uh, follow the situation here, we have a square base. So the length of this is equal to S. The length of this is also equal to S. And then the altitude, it's from this point here up to this point, okay? Assuming that this origin here, the 0, 0 coordinate of your Cartesian plane, it's at the center of your square base. So that guy there is equal to H, okay? So that is the this is the pyramid with square base in the three-dimensional view, okay? Now, let us look at the two-dimensional view. So what we're going to do is to look at this particular portion of the pyramid. So in here, you will have um, this part here. So this is on the side of that face, okay? And then in here, this is the part of the floor. And then on that face, you have this part here, okay? So basically, if we look at the top view, okay, we look at the top view of this pyramid. So you'll just see the square. And then we look at the floor of your pyramid. So this is the floor of your pyramid, okay? So um, the orange there at the bottom is it's this guy here, okay? So meaning this part here, this is the center, this is the portion of your x-axis. So this is the x-axis, this is the x-axis here. And you are not seeing the y-axis because it's directly on top, okay? So you are looking from the top of the pyramid, okay? Okay, so now let's look at the front view and that portion of the pyramid, this cross section here, the orange part, okay? So we have the orange part only. So for the cross section, we have the following. So this is the top of that, okay? So it's this part here, and then you have this, and then of course you have this, and you will see this triangle here. With this representation, this point here, this is the point s over 2 comma 0. And also, of course, this guy here, this is negative s over 2 comma 0. So at the bottom, okay, at this particular bottom, the side length, it's equal to s. correct? And then this point here, this point here, this is the point 0, comma h. So that the height, okay, the height that we see, okay, in here or in this part here, okay, it's that part there. So let me label that. So from that top up to this. So this guy here, the total length will be, or the total height will be h. And of course, this total length here, it's equal to s. Okay? Now, looking at this portion here, and then we look at the cross section, um, take note that at different heights from your pyramid, okay, the length of the square will be different also. So what I'm saying is if you have this, okay, at this height, say at this height here, okay, at this height here, it will be somewhere in here, okay, all right. So you have there. So that is your uh, square at this particular height in here. So at this particular height in here, this is your square. And it's not equal to S. It will be less than S because as you can see, you have this triangle here and up way here, it's shorter compared to the base in here. Okay? But this is what we know. This endpoint here will have a coordinate x comma y. Okay? So meaning in here, we have here the x on the x-axis. Okay? So we have there on the x-axis, that's your x. Okay? And therefore, it's from this point. Okay? It's from this point up to this point. This is x. And therefore, from this point up to this point, this is also x. So that the total length for this green part here, it is equal to 2x. Meaning, if we look at this three-dimensional pyramid here, you have this is x or 2x. This is also 2x. So the area of the square at that particular height of the pyramid will be 2x quantity squared. Okay? So again, this side length here, this is 2x. This here, this is also 2x. Therefore, the area uh, at that particular height on the pyramid, the area of the base will be 2x squared. Okay? The question is, we want to find an area function. Okay? We want to find an area function. So this horizontal here, you can think of it as your strip that moves going up and down, that moves vertically. So at another height, maybe somewhere here, you will have a different, of course, definitely you will have a different area of the base. At this height here, you will have a different area of the base. But if you represent that as x comma y, then the total length is still represented by 2x squared. But again, this is horizontal. The motion is vertical. We need a variable y as the variable of integration when we convert everything to definite integrals. So our first job is, well, how do we write these coordinates in here? Okay, how do we write these coordinates in here? Now, keep in mind, you have this point here, up here, 0, comma h, and you have this point here, okay? s over 2 comma 0, you can write the equation of the line that contains that segment. Okay? We can use two-point form if you remember that. Let me recall it here. P1, x1, comma y1, and then P2, x2, comma y2. Okay? So the two-point form will be, you can write it as y minus y sub 1 equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1 times x minus x sub 1. So two-point form of the line. And for this segment in here, okay, for this segment in here, we are given 2 points. This point here and this point here. So following the two-point form, we will have y minus h. This is equal to 0 minus h divided by s over 2 minus 0 times x minus 0. Okay, so I used my P1 to be this, I used the P2 to be this. So if we follow that, we will end up with this equation. Okay, so if we simplify this, we will get the following equation. Y minus h equals negative 2hx over s. Okay, and therefore we now have an equation relating the coordinates x and y. It's this guy here. Okay, and we need now the variable y. So we have x in terms of y. Particularly, we want 2x. That's your area. This is the area function, the 2x squared. So we need the 2x. So if we do that here, we can get 2x. We can isolate 2x. 2x will just be negative s over h times y minus h. Okay? Therefore, what is now the volume? We are now ready to write the volume. So volume equals the integral. So the horizontal strips, these horizontal strips again moves vertically. So the lowest point will be at this point, y equals 0. The highest point will be at this point, and this is at y equals h. So this will be from 0 to h, and then area function. Okay, the area function, we will write this as a of y, and then we have the dy. But this is now equal to 0 to h. A of y, it's 2x squared. So we have this. We have quantity s over h times y minus h, quantity squared dy. So this is just integral from 0 to h of s squared over h squared, quantity. Let us expand this y minus h here. Let us expand this y minus h here, quantity squared. We'll get y squared minus 2hy plus h squared. And then you have the dy. Okay? And then we integrate this. We integrate this. We can take out the constant s squared over h squared. Then integrating, we will have y cubed over 3. In here, you have minus 2hy squared over 2. Then plus h squared y. We evaluate this from 0 to h. And this is equal to, Let me just write it here. This is equal to, so you have s squared there. The denominator here, by the way, it's squared, h squared. So s squared over h squared. And then at h, you will have h cubed over 3. And then on the second term here, this will cancel this. So we will just have h times h squared. So h times h squared. And then plus, you will have h squared times h. And then at 0, everything is 0 there. But as you can see, again, this guy here will cancel this guy. So we'll just have s squared over h squared times h cubed over 3. And if you simplify this, this is s squared h over 3. And this is precisely the formula for the volume of the pyramid. I hope you remember this formula from your secondary math or primary math. But this is the formula. Okay? So in here, find the volume of the solid whose base is the region bounded by the curve y equals x squared and the x-axis from x equals 0 to x equals 2, and the cross sections taken perpendicular to the x-axis are squares. Let us try to illustrate this. Suppose this is your x-axis, this is your y-axis, and you have this y equals x squared. So in here, you have y equals x squared. Okay. Y equals x squared. And the x is from 0 to 2. So from this point here, let me change the color. This is your y equals x squared. From this point here and maybe up to this point, this is your 2. Okay? So let us adjust this. So at 2, maybe we have this. So we have this region here. Okay? So this is y equals x squared. Cross sections are taken to be perpendicular to the x-axis. Okay, cross sections are taken perpendicular to the x-axis. And these cross sections are square. Okay? Now, let me remove the shade here. Okay, let me remove this shade here, or maybe I'll just do this. So this is y equals x squared. So what does this mean? At this point, it's just a point. Okay, at this point here, it's just a point. If we look at this point here, of course, this will be the height. Okay. Cross sections are perpendicular to x-axis. So you will have something like this. This is a cross section. Okay. If you have this point here, cross section will be perpendicular to x-axis. So you will have this guy here. Okay. And at the very end here, we have this and we have this. And of course, we have this guy here and towards this. Okay? So what can you imagine the solid? Let me rotate this a bit. Okay? So you have this guy here. Let me redraw that. You have this guy here, and then um, you have this guy here. Let me adjust this. So at some point, so that this guy here will be somewhere at the back. Okay. Then here you will see this guy here. And then, so this guy, it's something like this. Okay. Um, Imagine a musical horn. Is it called tuba? Okay. That instead of circular, you have square. Okay. Instead of circular, you have squares. Something like you have that something like here and then something like here. Instead of circular, okay, instead of circular, you have is square instead. That's the solid. Okay. So I hope you can imagine um, the solid I'm trying to draw in here. This guy here, it's just straight, this part here. But anyway, we don't know, well, I can imagine what the solid is, but our goal is to find the volume of this solid. Okay? So the question is, what will be our area function? So if we go back to this, if we go back to this guy here, okay, so let me redraw this. So you have this y equals x squared. This is your x equals 2. This is the x equals 0. Okay. So for this guy here, it's this part. So you form that square. But what you know is at this point, okay, the area of that particular square, it's just 2 squared. Actually, is it 2 squared? No, it's not 2 squared. It's 4 squared. Because from here up to here, the length will be equal to 4. So this guy here, the length is equal to 4, and therefore this guy here is also equal to 4. So it's 2 squared. At this particular point, at this particular point, you have this. If this were your x, then here you have the point x comma x squared, meaning the height will be x squared. And therefore, the area of the square base there, or the cross section, the area of the cross section will be x squared squared. Okay? So at this guy here, you have this guy here. So this uh, from here up to there, it's still x squared. So the area, the area of the cross section, which is in terms of x. Why in terms of x? The cross sections are perpendicular to x-axis. This is your x-axis, so perpendicular to the x-axis. So it seems that your squares are moving from this point up to this point. So the motion is horizontal here. Okay? But looking at this, the approximating slab is vertical. So if the approximating slab is vertical, then the variable of integration must be in terms of x. And therefore, this area function will be x squared squared. Yes, question.
Yeah, could you repeat why it's in terms of x and not y?
Sorry, can I repeat what?
Could you repeat why it's in terms of
Okay,
x?
so in here, the, the, the cross sections are taken to be perpendicular to the x-axis. So this is a cross section. If you have another cross section here, it's still perpendicular to x-axis.
Okay, perfect. Thanks.
Okay, and that's one way to think of it. Another way is, since you know that they are perpendicular to x-axis, as a slab, like this square here, it's your slab, it is vertical. Okay, so the approximating slab is vertical,
Oh, okay. Okay, thanks.
which means you use variable x. If you recall our discussion on area, if your approximating rectangles are vertical with respect to x, if your approximating rectangles are horizontal with respect to y. Same is true with this. If the approximating slab is vertical with respect to x. Okay? So the length of this slab is x squared, and therefore the area of this slab will be x squared squared. So that's your area function. This slab will run from 0 to 2. So the volume will just be the integral from 0 to 2 of a of x dx, or it's the integral from 0 to 2 of x to the 4 dx. So calculating, this is x to the 5 over 5 from 0 to 2. So this is 2 to the 5. That's 32 over 5. So this is the volume of that solid. Okay, questions?
Sir?
Yeah,
Yeah, why is it even x squared in the first place?
because that's what is in here.
Oh, okay. Yeah, okay.
Yeah, yeah,
Sorry. Thanks.
you're welcome. Other questions? Now, let us talk another type of solid. Okay, solids of revolution. So in this course, we will only discuss a special type of these solids called the solids of revolution. Okay, a solid of revolution is a solid that is generated by revolving a plane region about a line called axis of revolution that lies in the same plane of the region. So for example, you have here a rectangle, including all the points inside that rectangle. We revolve it about this um, about this axis here. If we revolve it, we will get a circular cylinder. Here we have a rectangle. Okay, we revolve it about this axis. After revolving it, we will get a right circular cone. Okay, so in here, as you can see, the axis of revolution, it's either, well, in this case, it's on a side of your region. The region here, it's rectangle. The axis of revolution, it contains this side of the rectangle. In here, you have this triangle. The axis of revolution, it contains the side of this triangle here. Okay? And then, say in here, we have a semicircle. This is your diameter. Okay? The axis of revolution is on this diameter here. If you revolve this, you will get a sphere. Okay? But there's also a possibility that you have a plane region. Okay? This is a rectangle. And your axis of revolution does not intersect your plane region. Just like this. This is your rectangle. Your axis of revolution is here. So when you revolve this, what you will get here is like a tube. Okay? Because when you revolve this, only this part here will create a solid. And all the parts on this, it will not create anything. It's just a space. That's why this hole here in the middle is created. Okay? So either your axis of revolution contains a side, okay, a side of your region, or a single point of your region, or does not contain any part of your region at all. Now, some students were asking, can I have an axis of revolution something similar to this? Imagine, if you revolve this, okay, all the points that are in here will create some solid, but eventually at some point when it passed through this part here, it will bump the solid that was created by this part of the region. Okay? So intuitively, we cannot do that. Or at least in reality, we cannot do that. That's why our axis of revolution in here, either they're just the side of your region, just like this, or this guy here, side of the region. Possibly, it contains a single point. Okay? In one of the examples, maybe later, you will see that. Or your axis of revolution is totally not intersecting the region. So the axis of revolution, it's totally not intersecting the region. So those are the cases that we will consider. They are called solids of revolution. Okay? For these solids of revolution, we will have three methods. We'll do two methods today. Okay? So the first problem for the solid of revolution. Let F be continuous and non-negative on AB, and let R be the region that is bounded above by y equals f of x, below by the x-axis, and on the sides by the lines x equals a and x equals b. So this is your function here. You have x equals a, you have x equals b, and you have this region. The boundary below, it's the x-axis, so it's this guy here. Now, Find the volume V of the solid of revolution S that is generated by revolving the region about the x-axis. So the axis of revolution is the x-axis. And take note that the x-axis, it's the boundary. It's just a side of your region. So revolution is possible. Okay? So when you revolve this, you will have a solid that looks something like this. It's a solid. There's no hole in the middle. Okay? Because all the points on this region will create its own ring. Okay? But all the points here, they are really close to each other. I mean, consecutive points are close to each other. So those rings actually create um, a solid. Okay? So you have here a solid of revolution. One thing to keep in mind, the cross sections will always be circular cylinders. In fact, a thin circular cylinder. We call it a disc. So this guy here, it's a disc. Okay? So this is just a disc. We can get the area of a disc, a circular disc to be more precise. Okay? And once we know that, you have the area of the disc. So area, let me just write A here, area of disc, area of discs. Okay? If we know that, then the volume will just be the integral. Okay? This is the left side, which is at x equals A. This is the right side, which is at x equals B. This disc, you can move it from x equals A up to x equals B. So the volume will be from A up to B. And this area of the disc at this particular x. So you have A of x, and then you will have the dx. And take note, we just follow the same, we just followed the same formula as in the first part. Okay? Area of the disk, we have the area function. But what's special in here is we can actually specify what the area of the disk is immediately. Area of circle, it's pi times the radius squared. And if you are looking at this, what is the radius of that circle? It's from this point up to this point. Okay? So from this point up to this point, that's the radius. But this point here, it's a point on your function f of x. So the radius is actually f of x. So this area here, okay, this area here will just be pi times f of x squared. So this is what we're going to derive. And the derivation, it's the same as the ones that we have done. So this is actually the shortcut because we did the first part of this lecture, the derivation of the first part of this lecture. Okay? So observe that the cross-section perpendicular to the x-axis at the point x is a circular disc of radius f of x. The area of this region is a of x equals pi times f of x squared, and therefore the volume is given by this. Okay? Questions? First example, derive the formula for the volume of a sphere of radius r. Okay? So how do we derive the formula for the volume of this sphere? If you look at this, you have a semicircle, you revolve about this, okay, where this axis of revolution is along the diameter. When you do that, you will get a sphere. So basically, we'll just use a semicircle and revolve it, and we will get a sphere. That's how we're going to derive the volume of the sphere. So let us sketch. This is your x, this is your y, and consider the function f of x. This is equal to square root of r squared minus x squared. So this is this. So this is negative r, this is r, this is also r. Okay? So pretend that that's a semicircle. Let me just adjust. Maybe this will give us a better semicircle. Yeah, whatever. Pretend that it's a semicircle. Okay? Okay, consider f of x. So consider the region. So let R be the region. Region below the graph of y equals r squared of r squared minus x squared over the interval negative r to r. So you have this region here. Okay? And then the sphere of radius r can be obtained by revolving capital R about the x-axis. The x-axis. So we revolve this. Okay. If we look at this part here, okay, if we look at this particular rectangle in here, when you revolve this, of course, what you will get is a circular disk of radius r. Okay? You will get a disk of radius r. Actually, no, it's not of radius r. Of radius this point up to this point. Okay? You will get a disk of radius this point. It's not seen there. So this point here up to this point. Okay? But if this were x, I don't think it's if this were x in here, then this guy here has coordinates x comma f of x. Correct? Just like in here. If this were x, Then this guy here will have coordinate x comma f of x, and the radius of this particular disk is f of x. So the radius of this disk here, it's f of x. But our f of x, it's this guy. Take note that this guy here, this has equation y equals square root of r squared minus x squared. So the volume is, so v, this is integral from 0 to r. Sorry, it's from negative r to r. So this slab here, you can move it from this point up to this point. Okay? So this is negative r here. If we look at this, particularly this rectangle here, you will still get a disk in here. Okay? This is still a disk. So you will move the disk from this negative r until to the positive r. And therefore, the volume will just be the integral from negative r to r of pi f of x squared. Okay? Let me write that. F of x quantity squared dx. But f of x, it's this guy here. So integral from negative r to r of pi times square root of r squared minus x squared squared dx. Or this is equal to the integral from negative r to r of pi times r squared minus x squared dx. So if we integrate this, we will have pi r squared x minus pi x cubed over 3, evaluated from negative r up to positive r. Let me adjust this. Okay. So if we do the evaluation at r, we will have pi r squared times r minus pi r cubed over 3. At negative r, so minus. At negative r, we have pi r squared times negative r minus pi times negative r cubed over 3. And try to calculate this. You will get 4 pi r cubed over 3. Okay? Questions? Okay? Another example here. Find the volume of the solid that is obtained when the region under the curve y equals square root of x over the interval 1, comma 4 is revolved about the x-axis. So find the volume of the solid that is obtained when the region under the curve y equals square root of x over the interval 1, comma 4 is revolved about the x-axis. So this is your x here, y here, and you have the square root function. It's something like this. Okay, and then say this is your 4 here. Okay, and say this is your 1. So you need this region here, here, here. So you need this region here. This is your region R. And then your axis of revolution is the x-axis here. So you want to revolve about the x-axis, which means, of course, this is your region R. Okay, if we get a rectangle, approximating rectangle here, and we revolve this rectangle, you will be able to create the disc. Okay, and you do that to all parts here from 1 up to 4. So again, this guy here, it's y equals square root of x. So you see, we don't even need to know what the solid is. We don't even need to identify the shape of these solids. Okay? So you have this disk. This disk moves from -1 up to positive, from 1 up to 4. So you know your limits of integration. So volume, it's just the integral from 1 up to 4. The radius of this disk will be square root of x. Okay? So we will have pi times square root of x squared dx. Okay?
Sir?
Yes.
Yes, why is it squared?
Again, the disk, the area of the disk,
Oh, PR2.
pi
Okay,
r
got it.
squared,
All right, thanks.
and the radius is square root of x. And therefore, this guy here we can easily solve. So it's the integral from 1 up to 4 of pi x dx. So this is just pi x squared over 2 from 1 up to 4. So this is pi times, or pi over 2 times x squared, that's 4 squared minus 1 squared. So 16 minus 1, 15. So you will get 15 pi over 2. So this is the volume of that solid. Okay. Questions? Now, the second problem is the following. So in this illustration here, I said that solids of revolution can be obtained by doing this, something like this. The axis of revolution is contains the side of your region, but there's also those solids obtained by revolving a region, okay, about an axis of revolution which does not contain any part of the region, just like this. So we'll just derive the um, the volume. We'll derive a formula on getting the volume of these kinds of region, solids. So for this, okay, let f and g be continuous and non-negative on AB. Okay, and suppose that f of x is greater than g of x for all x in the interval AB. So remember this region here. We discussed this last time. So we let R be the region that is bounded by y equals f of x, y equals g of x, and the lines x equals a and x equals b. So find the volume of the solid of revolution S that is generated by revolving the region R about the x-axis. Okay? So you have this region. Your axis of revolution is here. It does not contain um, the region or any part of the region. So when you revolve this, you will get some holes or some hole in here. Okay? So in order to get the volume of the solid generated here, okay, one way to think of this is to get the volume of the whole solid if you only have f of x, okay, and subtract the volume of the solid if you only have the g of x, okay. The solid generated by g of x or the region below g of x, that's the actual whole. So if you subtract that, okay, you will get a formula or you will get the desired solid. So when you revolve this, the slabs will be called a washer. Okay? A washer, it's just a solid with it's just a disk with a hole in the middle. Okay? It means that your compact discs, okay, the one with the hole in the middle, I hope you still remember that. Your DVDs, okay, that's actually a washer. It's not really a disk, quote unquote. Mathematically, it's not a disk, it's a washer. Okay? So, how do we get the area of um this washer here? Well, similar to what I mentioned earlier. You get the area if you calculate this for your f of x, and then you subtract the area if the area generated by the g of x. Okay? So, observe that the cross section of the solid taken perpendicular to the x-axis at the point x is a washer, this with a hole in the middle. Its area is given by this, pi f of x squared minus pi g of x squared. Okay? Or if you factor out pi, you will have pi times f of x squared minus g of x squared. So you know the area of this solid. Therefore, of this disk or of this washer, okay? You know the area of this washer. We can now apply the concept that we learned at the beginning. And therefore, the volume will just be the integral from a to b pi times f of x squared minus g of x squared dx. Okay? So again, this is still your the volume. This is still your integral from a to b of the area function a of x dx. But again, we know what a of x is. It's this guy. That's why we can substitute it immediately. Okay. Now, it is possible that the axis of revolution of a solid of revolution is not the x-axis. However, the cross sections are still circular disks or washer. In these cases, make sure to use the proper radius or the proper radii in the area function. Okay? Just remember, the area function for the disk, pi radius squared. And then for the washer, you have here pi bigger radius squared minus smaller radius squared. Okay? Yes, question?
How do we know the difference between a washer and a disk, like when to apply which one?
When you have the region and you try to revolve it, and then you get your approximating rectangles, of course, those approximating rectangles, when you revolve it, it will create some solid. Okay? Like this. This is your approximating, um, this is just a segment here. Okay? But when you revolve this, take note of this space here. It will create a hole. Unlike in the other guy, okay, you have this complete here. So if you revolve this, you won't get any hole. Okay?
So to recap, it if it touches directly the x-axis, then we use what's called then we use the disk method.
If,
Whilst if
yeah,
there's a space from the x-axis, then we use a washer method.
yes. But
Perfect. Thank you, sir.
you have to completely you have to consider the interval also. Okay? So what I'm saying is, suppose your, let me go to this. Suppose you have something like this. Your region is like this, and then suddenly it has something part in here, and then your axis of revolution is this. Is still the x-axis. Of course, at this point or at this part here, there will be no holes. And then at this point, there's still no hole, but at this point, you will create a hole. Okay? As a whole, take note of this, as a whole, you need to use washer's method. But what you can do also is to divide this into two parts. This part, and then this part. So that on this part, you use your this part, you use your washer. Okay? Let us consider some um, examples here. Find the volume of the solid generated when the region between the graphs of the equations f of x equals 1 half x squared and g of x equals x over the interval 0, 2 is revolved about the x-axis. So let's start with f of x equals 1 half x squared. So say this is 1 half, this is 1, this is also 1 half on the x-axis, this is 1. So this is your x. We need until 2. So we have here this is your 3 halves and this is your 2. Okay? So 1 half x squared. So for that function, you will have this guy here. Oops. say something like that. And then g of x equals x. So g of x equals x. We have something like this. Okay? And that x equals 2. So this guy we extend. We need to extend this parabola here. Let me just approximate this. So we have at x equals 2, it's somewhere here. Okay? Look at that. And then we have this x equals 0. So this is your region here. Okay? That's your region. Your axis of revolution, it's your x-axis. Okay? You're approximating rectangles. Let's say, let's get this. Approximating rectangles. So if you revolve this about the x-axis, this is what you will get. For this, sorry, that's too exaggerated, but let's see. You will have something like this, okay? But there will be a hole in here. This is the hole, okay? So I'll color the hole. This guy here, it's a hole. So you will have a disc. And all throughout, you will have some holes. For example, if you get the washer on this, okay, if you get the washer on this, you will have a small washer, okay, but there will still a hole in the middle. So this guy here will create the hole, okay? So this guy here will create the hole. But anyway, remember this remark. Bigger radius squared minus smaller radius squared. Let's look at that. So this blue here, this is your y equals 1/2 plus x squared. On the other hand, this guy here, this is your y equals x. All throughout, y equals x is lower than your parabola. And this is where your axis of revolution is. So the bigger radius is this guy here. So bigger radius. And the smaller radius will be this guy here. This guy here, smaller radius. Okay? Now, starting this point, I'm going to write this bigger radius and smaller radius, especially for the method of this or washers. Because you will have to determine the exact radius or radii. In here, the bigger radius, it's from this point up to this point. But this is just the x-axis, so we're totally good up to now. Okay? Hence, the volume will just be the integral from 0 to 2 of pi times bigger radius here. This is simply your f of x. And the smaller radius, this is simply your g of x. So bigger radius squared, f of x squared, that's 1/2 plus x squared squared minus smaller radius squared, that's just x squared here. And then we have the dx. So if we calculate this, okay, we have the integral from 0 to 2 times pi. Let us expand this guy here. So we will have 1/4 plus x squared plus x to the 4. And then we have minus x squared dx. So try to expand this. Okay? Try to expand this. Okay? If you expand this, you will get this guy. And well, you can cancel x squared and x squared here. So we can minimize the computation. So we have pi, and then integrating, we will have 1/4 x plus x to the 5 over 5 evaluated from 0 to 2. Again, we cancel this and this. So at x equals 2, we will have 1/4 times 2 plus 2 to the 5 over 5, and then minus 0. So let's see. We will have pi times 1/2 plus 32 over 5. So if we simplify this, we have pi, and then we have over 10. So this is 5 plus 64. So this is equal to 69 pi over 10. So this is the volume of that solid. Okay. Questions? Next example. Find the volume of the solid generated when the region under the curve y equals x squared over the x-axis, okay? Over the interval. Okay. So find the volume of the solid generated when the region under the curve y equals x squared over the x-axis over the interval 0, 2 is rotated about the line y equals -1. And then the other problem here is if the axis of revolution is y equals 5. So this time, the axis of revolution, it's not the x-axis. The x-axis, listen, the x-axis has equation y equals 0. This time, the axis of revolution, it's not y equals 0. Okay? So, keep your attention in this solution. We have this. We have y equals x squared. So, y equals x squared. Say it's something like this. The interval is from 0 to 2. So, suppose this is your 2. Okay? So y equals x squared. The interval is 0 to 2. So here's your region. Okay? And let us get some approximating rectangles. Because this is just the region. Okay? Now look at this. The axis of revolution. So for letter A, the axis of revolution is the line y equals -1. So suppose this is your y equals -1. So this is your axis of revolution. So this is your line y equals -1, and you will revolve, okay? You will revolve the region about this line. So it means that this line here will give you the center of your disc or of your washers. Okay? So look at this. If you revolve this, okay? If you revolve this, you will have the following washer. Let me use another color. So in here, you will have something like this. And since this is your axis of revolution and there's a space here, take note of that. This will be the hole. This will create this hole. Okay? So, this means that this is your bigger radius, and then this is your smaller radius, this guy here. Correct? Again, the equation of your x-axis, it's y equals 0. It is still a function. But the point here, you have to identify properly the bigger radius and the smaller radius. So what is the bigger radius? So bigger radius, this is equal to your x squared. It's from this point up to this point here, the center. So it will be x squared minus -1. Or this is equal to x squared plus 1. So from this point up to the x-axis, it's your x squared. But you have this one here, so you have to add that. But more formally, the distance from this point here up to this point, it's this point minus this point. But this point, it's -1. So you have that x squared minus -1. Okay? For the smaller radius, you will have 0 minus -1. Because again, the equation of the x-axis, it's y equals 0. So you have 0 minus -1 here. And that's precisely +1. That's precisely the radius in here, the distance. Okay? Therefore, volume will be the integral from 0 up to 2. So 0 up to 2 of pi times bigger radius squared, that's x squared plus 1 squared, minus smaller radius squared, that's 1 squared. And then you have your dx. Okay? So I'll leave this one to you. Continue. Okay? So that's for letter A. Let's do letter B. So you still have that, okay? That same function. So this guy here, this is your letter B. You have this y equals x squared, okay? This is your 2. 2 squared, so let's just have this. 2 squared here, this is equal to 4. Correct? 2 squared, it's 4. It's not obvious, but say it's actually 4. And then your 5, it's somewhere here. Okay? So the region, it's still the same. Okay? Your approximating rectangles, it's still the same. Okay? But take note of this. Your axis of revolution is up here. It's at y equals 5. So you revolve about y equals 5. Okay? So when you do the revolution, you will get this washer here. Okay? And then, of course, there will still be this hole. There will still be this hole here. Got it? Okay. Now, what is the bigger radius? The bigger radius, it's from this center going to this part, correct? So it will be from this up to this. This is your bigger radius. And then the smaller radius will be from this point up to this point. So this guy here, this is your smaller radius. So it's just from this point up to the function. So let's write them. Bigger radius. This is from y equals 5 up to y equals 0. So that's just 5 minus 0. And then the smaller radius, it's from y equals 5 up to y equals x squared. So that's 5 minus x squared. And therefore, we have the following. Volume equals. I'll put pi outside. So I have pi from 0 to 2. Bigger radius squared, it's just 5 squared, minus smaller radius squared, it's 5 minus x squared squared. And you have the dx. So this will give you the volume of this. Okay. Questions? Okay. Now, in our examples, the axis of revolution is either the x-axis or anything parallel to x-axis. In fact, this example, I just gave two axes of revolution which are not the x-axis, but it has of the form y equals some number. So y equals -1 or y equals 5, okay? These lines here, they are parallel to x-axis. So the axis of revolution, okay, it's a horizontal line. So when you revolve the region, what you will get are vertical approximating slabs. Particularly for this, you have a vertical washer. And in the first problem, you have the vertical discs. Of course, there are some cases where you need to do you need to use y as your variable of integration. So if the solid of revolution is obtained by revolving a plane region about a vertical line, okay, one can deduce the following formulas. So you will have this. Okay, this is for your disk method. So this is your region, the axis of revolution, it's this line here. So when you revolve this strip here, okay, this strip here will create this horizontal disk. Or if you have the washers, so you have this region, you have this strip here, your axis of revolution, it does not intersect your region. So when you do the revolution, you will get some holes. Okay? So this strip will generate this washer. Okay? But keep in mind, for the washer, bigger radius squared minus smaller radius squared. Okay? For the disk, there's only one radius, so it's totally fine. But you have to know what the actual radius is. Okay? Let's do this example. Find the volume of the solid generated when the region enclosed by y equals square root of x, y equals 2, and x equals 0 is revolved about the y-axis. So let's draw the region. So you have your x-axis here, you have your y-axis here. This is your square root of x. Okay, let me use a different color. This is your y equals square root of x. Y equals 2, let's say This is your y equals 2. Okay, this is your 2. So the line will be something like this. Okay. And then your x equals 0, it's this guy. So this is your region. Okay. This is the region here. Now, the axis of revolution, it's the y-axis. So we are revolving about the y-axis. So let me remove the shade here. But anyway, so we are revolving about the y-axis. In this case, your approximating rectangles will be horizontal. The needed approximating rectangles will be horizontal. So if you revolve this, you will create this disk here. Okay? So if you move this disk, it's from this point up to this point. So the disk, it's horizontal. Therefore, your variable of integration must be y. And therefore, your function here, particularly this function, it must be written as x in terms of y. So in here, you can write this as x equals y squared. And you got a disk in here, so the formula for the volume, this is just the integral from this point up to this point. So you move this disk from this point up to this point. Let me draw another disk in here. Say this is your disk. So you will have, say that's your approximating rectangle. So after the revolution, you will create this disk, etc. But anyway, the volume will be the integral from 0 to 2 of pi. And what's the radius? It's from this up to this. So the radius will be from this up to this. This is x equals 0. This is x equals y squared. So from x equals y squared up to x equals 0. That will be the radius. Correct? So this is just y squared squared dy. So if you integrate this, you'll just get pi y to the 5 over 5 from 0 to 2. And this is just 32 pi over 5. So this is your volume. Okay? One last set of example. Find the volume of the solid generated when the region between the curve y equals x squared
Sir,
and the x-axis. Yeah.
can you go back to the formula for example number 1, please?
The formula? This one or the one before?
That's perfect. Thanks.
Okay. So find the volume of the solid generated when the region between the curve y equals x squared and the x-axis over the interval 0, 2 is rotated about First, the y-axis. Second, the line x equals -1. Third, the line equals x equal the line x equals 3. Second, the line x equals -1. Third, the line x equals 3. So let's see. We have, this is your x-axis. This is your y-axis. You want y equals x squared over the interval 0, 2. So you have this 1, 2. You want the region, okay? Between y equals x squared and the x-axis over the interval 0, 2. So you have this region here, okay? Okay. So first, for letter A, we want the revolution, the axis of revolution to be the y-axis. So first, you want the axis of revolution to be this. So your approximating rectangles must be horizontal. So this is one approximating rectangle. So if we revolve this, we will get a disk. So let me just let me draw this part here. So when you revolve this, you will get a washer. And then the hole is somewhere here. We consider the bigger radius. So the bigger radius, it's from the center, that's the axis of revolution, up to the farther function. So it's not it's not clear there, but it will be somewhere. So from the axis of revolution to that farther function, so this is your bigger radius. And the smaller radius will be this guy here. From the center, oops. So from the center up to the function. So this is your smaller radius. So let's write that. Bigger radius, it's equal to this guy, x equals 2 minus the y-axis, which is x equals 0. So it's just 2 minus 0. And the smaller radius, it's from the function minus x equals 0. So you have here, so you need to write y equals x squared in terms of as x in terms of y. Take note of that because you are doing variable y here. Okay. So in here you got y equals x squared, but this is the same as your x equals square root of y. And we only take the positive side because anyway, we are just interested on the interval 0 to 2. So the smaller radius will be square root of y minus 0. Now, the interval 0 to 2, it's for the variable x, okay? It's for the variable x. But we need the interval for the variable y because again, this is horizontal strips. The integration will be, or the variable integration will be y. Okay, so we need to identify the y coordinate when x is equal to 0. So it's this guy here, but it can easily be seen that this is equal to 4. Okay, and therefore the volume will be the integral from 0 to 4, okay, times pi, or the integral from 0 to 4 of pi times bigger radius squared. So 2 minus 0 quantity squared minus smaller radius squared. Square root of y minus 0 quantity squared. And we have the dy here. Okay? So let's just finish this integration in here. We have from 0 to 4. Okay? And then we have pi quantity 4 minus y dy. So integrating, we have pi times 4y minus y squared over 2 evaluated from 0 to 4. So this is equal to pi times 4y, that's 16, minus y squared, that's 4 over 2, okay? And that's just 2 there. So this is equal to 14 pi. So this is the volume of the solid generated when this region here is revolved about the y-axis. Okay? For letter B, let's do this. So this time, the axis of revolution is x equals -1. So the axis of revolution will be, say in here, this is your x equals -1. The axis of revolution will be somewhere here. Okay? So you should realize that the disk will be much larger compared to the previous one here. Okay? So the axis of revolution, it's still vertical. The approximating rectangles must be horizontal. So you have this approximating rectangle here. So if we try to revolve this, let me just try this here. You will still get a washer, okay? But now look at the bigger radius. The bigger radius is from this line here up to the center. So this is your bigger radius. And of course, the smaller radius, it's from the center and up to the function. Up to the function only. So this is your smaller radius. So if we write that, bigger radius, this is equal to x equals 2 minus x equals -1. So minus -1. So this is your 3. But anyway, I'll write in my setup, I'll write 2 minus -1. And then the smaller radius, it's from the function going to the axis of revolution. So in here, you will get square root of y minus -1. And then, just like before, this is the point here, 2, 4. So the limits of integration will be from 0 to 4 because still we have horizontal strips, motion is vertical. So from 0 here up to the highest point here, which is 4. Therefore, the volume will be integral from 0 to 4 of pi times bigger radius squared. So in here, I'll still write 2 minus -1 quantity squared minus smaller radius squared, which is square root of y minus -1 squared. And then we have the dy. So for this, I'll just set up this volume and you can evaluate this to find the actual volume of the solid. So we have this. This time, our axis of revolution is at x equals 3. So say this is your 3. The axis of revolution is somewhere here. So we want to revolve about this line, x equals 3. Still, approximating rectangles are horizontal. So again, if this were 4, the point here, it's the point 2, 4. Okay. Now, if we revolve, the disk will be, or the washers will be something like this. So you still have this hole in here. Okay. Now, what is the bigger radius and the smaller radius? The bigger radius is this time from the function up to the center. So this is the bigger radius. And the smaller radius, it's from this x equals to up to 3. This is your smaller radius. So we have bigger radius here. That's equal to 3 minus the function. So 3 minus the function. So it's 3 minus square root of y. And then the smaller radius, this is 3 minus 2. So 3 minus 2. And therefore, the volume will be pi integral from 0 to 4 bigger radius squared, that's 3 minus square root of y squared, minus smaller radius squared, 3 minus 2 squared. And then you have the dy. Okay?